Hello there, I'm Lee Holmes, and today I'm going to talk about some work that I did with Daniel Bohannon, a researcher at Mandiant, on PowerShell obfuscation detection. Now, as some context, this is the PowerShell download cradle, used by a lot of malware to either download additional PowerShell or, more often than not, an executable. Now, as defenders, people are writing lots of signatures to detect a string like this, but then attackers respond with something like this on the bottom left, which does basically the same thing, but looks like nothing you'd ever expect. Here's another example from APT32, a Vietnamese attacker also known as Ocean Lotus. Again, does the same thing, but good luck writing a signature against that. What if somebody decides to use only special characters as their obfuscation? What are you going to do then? Maybe all the variable names, maybe they're just white space. But hey, why stop at just variable names as white space? What if the entire PowerShell script itself was white space? So this is the kind of challenge that defenders are fighting. And as either an attacker or a defender, you might think, fatality, game over. But absolutely not. This stuff is not normal. If you look at it, you know that it's not a normal PowerShell script. You might not know what it is or what it does, but you know you need to dig deeper. So an approach that you can take is start to look at character frequency analysis. On the right-hand side, you see the character frequency analysis of one PowerShell corpus known as posh code. And on the left, you see the character frequency analysis of some of these obfuscated scripts. And you see that they're very different. Now, these lists of numbers, the information retrieval community has done a great job using something called COSINE similarity to determine how similar two lists of numbers are. And when you graph these against each other, you see that these symbolic and invoke obfuscation results are really, really dissimilar than a lot of other PowerShell scripts in the average PowerShell corpus. Now graph them all out and you see a really great grouping around 0.8. And when you take a look at everything below that in similarity, turns out that there's a lot of obfuscated stuff. Most of this is really just done for fun or whatever, but it seems like it's a really great result. But the thing is, we need way more data. So what we did is we scraped tons and tons of the internet. We got 4 gigs of content, nearly 500,000 scripts, 30,000 authors. We manually labeled 7,000 scripts, 30,000 command lines. And to put that 4 gigs in context, my lifetime history of PowerShell scripts is about 2 megabytes. So really, the amount of humanity is ridiculous. Now, with that data of what we actually have labeled as good and bad, obfuscated and not, we see that, hey, precision, which is when this algorithm thinks that something is obfuscated, it's actually pretty good. 90% of the time is correct. But the big issue is recall. It's only catching 37% of obfuscated PowerShell scripts. Hey, but this is PowerShell. We can do better, right? We got the power. Absolutely. The first thing we can start to leverage is PowerShell's tokenizer API. This shows you the difference between command names, parameters, operators, and all that kind of stuff. But we can also leverage the PowerShell AST, which is the abstract syntax tree. And this is a tree-like representation of everything in your PowerShell script. Now, based on these, we can start to look at obfuscation techniques. So is a script using a lot of different kinds of operators that are unusual, or very, very large arrays, really some of the deep, deep structure of a script. And based on this, we extracted 4,998 features that let us thumbprint a script. Now, based on these, we take every one of those features, give it a weight, add them all up, and get a result. If that result is greater than a certain limit, then we'll call that thing obfuscated. This technique is called a linear regression. It's really common in a bunch of tools like Excel and stuff, and that's classifying a domain of things into 2 categories based on this math of features and weights. We also apply a logit function, which is basically a compressing of a bunch of these numbers so that they're in a reasonable range. You combine that together and you get a statistical technique called a logistic regression. So hey, we got more math here based on the logistic regression. But we still have a huge problem. How do we decide on 5,000 important values? We're not just going to ask each other. At first it sounds great, but maybe not. The answer there is called a gradient descent. You start off with all of those weights as nothing, and then you run this prediction against the data that you've labeled and trained. When it's correct, great. But when it's not correct, you take the error and feed that back into all the weights that participated in that decision. You do this a lot. You got a bunch of data, you got a computer at your disposal, and that gives you weighting that properly separates the obfuscated from non-obfuscated content. Okay, so taking a look back at what we did, we started with a recall of 37% and 2% false positives, but using this much more rigorous technique, we are now 10 times better at finding obfuscated content with only half the false positives. So this is a really brief summary of what we did and presented this year at Black Hat 2017. So we'd encourage you to take a look at the white paper and also the recording on YouTube. Thank you.